Well, I assume we're recording now, so let's see if this one can actually get out there into the wide world. We're going to look at metals. First thing I'm going to say is you must read the essential readings. That would be chapter 5, ferrous and non-ferrous metals, because I don't cover everything in the readings. I just give you the overview of it so we can talk about it a bit later on. So do not rely just on the lecture. Go to your readings, please. So we're talking about metals in construction, and we know metals used absolutely everywhere in construction. So, you know, you've got steel-framed buildings where the metal is the structural element, taking all the loads and the weight, etc. You can have steel floors, you can have metal wall cladding, roof cladding, you can have metal doors, you can have metal handles, metal light switches. Reinforced concrete's got steel reinforcing bar in the middle of it. And then you come down to the smaller bits, so your screws and your nails and your brackets. You'll find it absolutely everywhere. Absolutely everywhere. Metal is. We break it down here into the most popular metals that we use. Can be split between a ferrous and a non-ferrous, which means a rusting and a non-rusting one, basically. Not 100%, but that's basically a good way to look at it. So I think the best thing to do is go in to have a look at the introduction. Basically, metals, you pick them just because they're strong and they're resistant to the weather. Forget the fact that they're going to rust and corrode. If you look after them properly and select the right type of metal, then you won't have that problem. Most common of these metals is steel, or more precisely a carbon steel, and then you follow it along with aluminium, copper tubing, lots of your plumbing and that's made out of copper. Stainless steel's becoming quite popular. Normally you'll find stainless steel where it's on show because it looks nice and shiny, so balustrades and things, but you can also find stainless steel as dowel bars joining a construction together at a movement joint. And other things, especially if you're in a very harsh environment, such as a marine environment. But each of them have got positives and negatives to them. Ferrous metals, they contain iron, and non-ferrous metals don't contain iron. Fantastic. So non-ferrous metals, they're the ones that have been used since we were crawling around as monkeys, I suppose. There's copper 5,000 years ago, which was the end of the Stone Age, as you see, and we're the Copper Age, which you don't normally hear that spoken about, but you do hear the Bronze Age talked about. Obviously, the Iron Age was before the Copper Age, I suppose, or afterwards. No, after, I think. Wrought iron, which was the first iron that was made, is an alloy, so it's got a little bit of carbon added to it. It's almost pure, just a little bit of iron. This is what kicked off the Industrial Revolution in Telford in Britain. Telford actually built the first cast iron bridge. Lots of original buildings were made out of cast iron. Only problem is it's a little bit fragile. It's not got good impact resistance. It doesn't bend very well. It'll snap. But that was the first one that came along. During the manufacturing process, things can be added to it to change its properties. So you've got slag added, gives you all iron resistance to corrosion, which it doesn't normally have on its own. Oxidation, corrosion, similar. But it's not very hard, and as I said, fatigue strength, wrought iron, you'll find it used for fences, railings. Occasionally, you know, in the old days, nails and barbed wire, but not so much more, not so much as you see there. So look around at old Victorian type properties and you'll probably see some wrought iron going around there. Ferrous metals themselves, common ferrous metals for you is generally alloys of steel, carbon steel, cast and wrought irons. They've all got good strength, good tensile strength and pretty good durability if you look after them well. Carbon steel is what we refer to as structural steel, so that's what you're seeing in all your steel frames and that going around. Very common in construction. Ferrous metals, you can make shipping containers out of them, and industrial piping, cars, you name it, they can be made out of this. Ferrous metals have got a high carbon content, which makes them a bit vulnerable to rusting when they're exposed to the atmosphere. There are two exceptions to that. Wrought iron does resist rust due to its purity, and stainless steel is protected from rust by the presence of chromium in the mixture, the shiny chromium. Most of the ferrous metals are magnetic, so it's a good way of checking which one it is if you've got a magnet in your pocket. So they're good for electrical things, and a few other bits and pieces you can do. So that's your ferrous metals. Then you've got ferrous alloys. This is a mixture. So alloy steels incorporate other elements such as chromium, makes stainless steel, nickel, titanium, which gives it makes it stronger and gives it more durability without making it heavier or anything. Stainless steels are an important alloy, which is steel with chromium. Alloy steels, we use them for machine tools, we use them in construction all over the place. They're just everywhere now. Cast iron itself is an alloy made from iron, carbon and a bit of silicon. Cast iron is brittle as hell. It's hard and it's resistant to wear, but it's really brittle. Used to be used for things like water pipes in Victorian times and a little bit after Victorian times. They tended to corrode away, unfortunately, with the sewers going down them. Coated steels, I think I've not done this one. No, coated steels, you basically take your steel and you can give it a coating. So you can coat it with plastic, you can coat it with a paint film, or you can coat it with zinc called galvanizing. There are a lot of coatings you can put on them, and the coatings are there to protect the steel from corrosion. And also the coatings can be coloured, so they can be for an architectural effect as well. But normally, as I said with timber, the coatings that are applied to metal is a preservative treatment to stop them corroding too much. Non-ferrous metals, they've got no iron in them, so they don't tend to corrode very much. So the metals include aluminium. Aluminium does corrode, but it just forms protective oxide film on its surface. Copper, lead, zinc and tin, they all corrode, but at different rates, much slower than steel does on its own. And then you get your precious metals like gold and silver, which you'll tend to find in electronic components more than anything, unless you're a sheikh down in Oman or Saudi Arabia, where you've probably got a solid gold toilet, possibly. The main advantages over ferrous metals is they're very malleable, they're workable. They're a little softer to work with, you can hammer them and bend them and shape them much easier. They've also, because there's no iron content, they don't rust very quickly. So they're ideal for areas where they're exposed to moisture or in aquatic environments. And we pick up gutters and things like that. Liquid pipes, copper liquid pipes you'll find quite often. Roof sheets, wall sheets. And they're not magnetic. So again, you can go in and check it with the magnet out your pocket if you want to. And making steel, well, this is going to be an interesting. I tried to do it, but I found a dodgy YouTube video, which I'll play so we all watch it now. I hope the little speaker works so that it gets recorded. So, and this is actually more interesting in me talking about it, really. Where do we go? You'll probably get an advert first.
Altos Hornos de Mexico, AMSA, is a fully integrated steel company which produces steel through processes ranging from the mining of iron and coal from its own mines to the completion of finished products. At the beginning of the steelworking process, the mineral ore is treated by pelletization and sinterization, while the coal is processed by coking. Coming from Hercules in the Coahuilan Desert, iron reaches the pelletizing plant as a sludge through a duct 14 inches in diameter and 180 miles long. This sludge is subjected to filtration. The water is recovered and the dry ore is sent to pelletizer discs to be mixed with binding agents to form small balls called pellets. At 1,300 degrees Celsius, the pellets are heat hardened before being sent to blast furnaces. Meanwhile, the coking plants receive metallurgical coal by rail from the Carboniferous region of Coahuila and treat it in vertical ovens lined with refractory brick. Through 18 hours of baking, the coal is transformed to coke, the basic fuel for the blast furnaces that produce pig iron or first fusion iron. During this process, various byproducts are obtained, among them coke oven gas, a fuel used in later stages of the steelmaking process. Another raw material for the blast furnaces is sinter, a porous mass composed of iron ore, flakes, and powder produced by the steelmaking process itself. Blending with lime, coke fines, and dolomite produces a mix that is hardened in the continuous chain oven of the sinter plant. Processed iron and coal, the basic raw materials for producing pig iron, are sent to blast furnaces consisting primarily of a large cylindrical structure over 160 feet high whose interior is lined with refractory brick. In the blast furnace, the iron oxides contained in the pellets and sinter, which are stored in the hopper's facility, along with limestone, dolomite, and coke, are reduced and converted to pig iron. Mixed in the proper amounts, these raw materials produce layers of various thicknesses when they are deposited in the blast furnaces through the charging system located on the top. Hot air is introduced under pressure into the bottom of the furnace, blasting the coke and smelting the iron ore in an environment of up to 1,650 degrees Celsius. In the lower part of the furnace, a graphite hearth or crucible receives the molten metal, which then is drained through tap holes and troughs and emptied into 200 metric ton capacity torpedo cars. In order to eliminate sulfur content, reagents such as calcium carbide and magnesium are applied to the pig iron in the desulfurization plant. The slag generated during the smelting is deposited in a slag pit to be cooled with water. It is later stored or sold as a byproduct. For the conversion of pig iron to steel, AMSA uses the oxygen-based technique of steelmaking called BOF, Basic Oxygen Furnace, as well as an electric arc furnace. BOF steelmaking begins by loading scrap metal into the converters, pear-shaped refractory-lined furnaces with capacities of up to 150 metric tons lined internally with refractory brick. When the proper amount of scrap metal has been loaded into the converter, molten pig iron is added by means of large ladles operated by traveling cranes. For refining, oxygen, argon, and nitrogen are injected into the mix under pressure through tubes known as lances connected at the top and bottom of the converter. After a period averaging 45 minutes, liquid steel is obtained. The steel is poured into large ladles and ferroalloys are added in order to adjust its chemical makeup to match the requirements of the material ordered by our clients. Production of liquid steel by means of the electric arc furnace is conducted by beginning with a mixture of scrap metal, iron briquettes, or liquid pig iron at a rate of 150 metric tons per casting. Scrap and briquettes are loaded by using baskets, while the pig iron is transported by a gutter to the furnace, where 3 graphite electrodes apply 140 megavolts of electric energy to melt the load and produce steel, which is emptied into special ladles. In order to produce specific properties, the liquid steel from both systems goes to the secondary treatment station, secondary metallurgy, ladle metallurgy, or chemical reheating. Likewise, liquid steel can be processed in the dual degassing station to reduce the content of hydrogen and carbon for applications with higher requirements. With the treatment completed, liquid steel is transformed into slab on equipment called continuous casting machines. In this process, as it passes through a series of rollers with a cooling system, it begins to solidify until it becomes a slab which is cut with oxygas to the required dimensions. The steel slabs are produced in different thicknesses, widths, lengths, and weights, and each piece is labeled for later processing by hot rolling. The hot rolling department, considered the backbone of AMSA operations, has a hot strip line which produces steel strip coils and 2 plate lines to produce steel plates in sheets or coils. On both lines, the slab is reheated to 1,330 degrees Celsius. Plate line 1 has 2 reversing mills that in a series of passes generate wide plate in the required thickness and width. On plate line 2, the 8-inch slab is laminated in a reversible Stecco mill, and the steel strip is temporarily stored in closed box furnaces to maintain temperatures above 1,000 degrees Celsius. Subsequently, an edger mill reduces the width of the strip to produce plate in sheet or coil. If required, the plate goes to the normalizing line, where through thermal treatment a uniform granular structure and greater hardness of the steel is obtained. AMSA is the only manufacturer in Mexico that produces steel plate, which is used for making farming and mining machinery, oil industry machinery, as well as heavy automotive and railway products. On the hot strip line, the slab is processed for the production of hot-rolled coil. First, the slab is reduced in the universal reversing mill to a thickness of 2 inches, and then on the M stand it is further reduced to 1 inch. The final thickness required by the customer is achieved on the 6 standing roll mill train. At the end of the hot strip line, there is a cooling system and a coiler. Hot-rolled coil, also known as full hard coil, is shipped directly to the customer or sent to other processes in the AMSA cold rolling departments. Through cold rolling, the thickness of the sheet is reduced, while at the same time modifying and enhancing its physical properties. The process begins with pickling in order to eliminate oxides through the use of a hydrochloric acid-based solution. Then the strip is cooled to room temperature in various mills in order to gradually reduce its thickness and achieve the desired specifications. In order to soften the material, the coil is annealed in a continuous heating oven at temperatures of up to 750 degrees Celsius. The steel strip then goes to the tempering mills, which give it a greater surface quality and the specified hardness required for the various applications. In addition, AMSA has skin pass and tension leveling lines which improve the surface quality of the hot-rolled and cold-rolled coil, respectively. In these units, a greater thickness uniformity is achieved, which is an essential requirement for manufacturers in the automotive industry, home appliances, and electrical steel. Furthermore, AMSA produces tin plate and tin-free steel, which are steels produced primarily for manufacturing of metal containers. In both cases, the cold-rolled coil is subjected to an electrolyte bath with tin and chrome, respectively. In addition to the hot rolling and cold rolling lines, there is a department of structural shapes. AMSA is the primary domestic manufacturer of structural steel for the construction industry. Production begins with the cutting of the steel slab into square pieces called blooms. Reheated in an oven at over 1,250 degrees Celsius, the blooms go through various rolling mill trains to produce structural shapes such as W shapes, C shapes, and angled L shapes. Built on advanced information technology systems, the AMSA productive chain requires support services such as industrial gases, electric power, water, transportation, and maintenance shops. Altos Hornos de Mexico operates its own power plants which use steam and internal combustion engines to produce electrical power and blast air for blowing into the blast furnaces. There are also units for the production of oxygen, argon, and nitrogen, as well as water treatment plants for raw sewage, industrial, and sanitary water. From the iron and coal mines all the way to the delivery of steel to the customer, the Altos Hornos de Mexico productive chain is backed by national and international standards. Implemented by highly trained technicians, employees, and laborers, the AMSA management system brings together strict standards for quality, health, safety, and environment. AMSA, quality with the strength of steel.
Well, I hope you found that quite interesting. Let's wait right to the end to see them doing a bit of construction stuff. That supplements quite well what's in the essential readings, so I hope you found that okay. We go over, you've got coated steels, which I'm not going to look at. I did mention those when they were coated. I've gone back on myself there. Oh yes, I did order those, didn't I? So if you hear any snoring, by the way, that's my little Cavalier Dexter. He's just stopped, actually. He obviously thinks I'm not being very exciting to himself. So that's the introduction to it. So what's the next thing we can do? I did the introduction. Hang on, bear with me. I just buggered it up again because I normally do that. I'm quite good at it. I pressed the wrong button, as usual. Aluminium. Aluminium, we know, is, as it says, it's the second most widely specified and used metal in the construction industry. It's got a high resistance to corrosion. It actually does corrode, but it forms an oxide protective surface. Most of the aluminium you'd actually see is surface coated. It may, you'll get the different colours and everything for windows and architectural features. And it may also just have a plastic coating on it if it's been used for some sort of cladding material. But it is resistant to harsh weather, so that's why it's used for exposed elements like the windows, roofing, cladding, that sort of thing. Structural glazing, so when you see these nice glass high-rise buildings, then that's an aluminium frame the glass is sitting in. It's strong, it doesn't corrode, and it's lightweight, so it's reducing the weight on the structural frame behind. You can get your prefabricated buildings, your dongers, that sort of thing. A lot of it's used in architectural hardware, shop fitting and partitions. If you go in an office and you can see, if you go into an office before it's been let, it's a completely open floor. You may be able to see a photograph of that in the photos I popped up there. And then it's subdivided into offices, areas and things by using aluminium framed structures, like giant construction bricks that kids would use, and then the panels are shoved into them, the glass is shoved into them, but they actually is an aluminium frame. They're very easy to put together. You can pop rivet them together or just use self-tapping screws. You'll use them, it's used a lot in plants, so you get ladders and scaffolding made of it, all again because of its quite lightweight and strength. Outdoor signage because it doesn't corrode, street lights because it doesn't corrode. It's normally in tube sheets, you can cast it. Air conditioning ducts, roofs, walling handles, very common as I said. It doesn't like salt water, unfortunately. The sodium chloride element in the salt water weakens the protective coating, the oxide film, so it will corrode itself there. So unfortunately it's not good for that. But aluminium, it's nice and strong. It's quite easy to dent though. That's the only thing. It hasn't got a good resistance to impact damage. Copper. Well, we like a bit of copper. It's nice and shiny when it's new, and then it dulls down as the surface oxidises, it weathers down. You get two main types of it. So, most common as pipes in water systems, gas systems, fire sprinkler systems. Quite often you'll find copper used in those. It's great for hot and cold water pipes. Chemo, look at that, you can all see that someone's after me. I'll talk to him afterwards. It's quite ductile, you can bend it nicely, it can shape it. If you've got sheets of it, you can shape it because it can be used for roofs and things like this. It is resistant to corrosion. It's very recyclable, and it's got quite a high value to it as well. It's easy to solder and join. A good tradesman will be able to do a lovely joint with it instead of relying on compression joints. They all make it ideal for plumbing, basically. Copper sheet is also used. You can use that for wall cladding if you want to make an architectural statement or as a roof. So it's probably not the most economic material to use for those. So if you do see copper up there nowadays, it's being done as an aesthetic addition. Historically, copper was used on roofs quite a lot, but not so much nowadays. You might find aluminium on roofs more often nowadays. Lead. Oh, I've done an awful lot of work with lead. It's a very dense, very heavy, soft, malleable metal. You bend it and shape it with your hands, although I don't recommend you do that without gloves on. It melts at a very low temperature. It's got really hardly any tensile strength, so it's not structural in any way whatsoever. But it doesn't corrode. Well, it does corrode, but it corrodes at an unbelievably slow pace. It's unaffected by lots of acids and chemicals. It's widely used for heavy-duty electrical cables, in batteries, in building construction, and it can be used as a solder as well. You'll find it's mostly used on things like roofs. They used to line water tanks with them. The Romans used lead as water pipes, both of which are not good ideas really, because it's not that good for you if you ingest it. It can't be used as a vertical cladding because it creeps under its own weight and normal heat, so it slowly creeps. But on a low-pitched roof, it's good. You can make ornate water goods, top of a rainwater pipe. You can put a lovely hopper on the top of it. You use it for flashings where, say, a chimney or parapet wall meets a roof surface, because it's so easy to bend and mould into shape. It gives a fantastic flashing, great joint. But it's not good for your health. I mean, it used to be added to paint at one time, and lead-based paints lasted longer than the modern paints we've got nowadays. But there's the list of the things that you can end up getting if you are poisoned by lead. That comes straight from that web link there of Safe Work Australia. Go and have a look a bit more about that if you want to. But there's a load of things there. Some of you might remember that there was quite a bit of concern up in Mount Isa a few years ago that everyone was getting lead poisoning coming out of the mine and refinery up there. Zinc. Okay. Zinc is been used for many, many, many years, hundreds of years, but today it's mostly used as a protective coating, commonly known as hot dip galvanizing. So galvanizing is actually zinc. You put it on steel to give it a protection against corrosion. The zinc, because of its position on the periodic table, will corrode before the steel corrodes. So it's known as I can't think of the word, my brain's gone. I'll come back to it. Preferentially, it will corrode. Sacrificial. It's a sacrificial metal or cathode. Anode. You can call it an anode if you want to as well. So it protects the iron, protects the steel, especially when they're in a very wet environment. In constructions, if you are using it, you can get it in sheets for roofing and for cladding, commercial buildings. Becoming a bit more common in residential building. Architects like it because it's got a nice look to it, a nice patina after a few years, just like copper does as well. Copper goes a little green. So zinc, and it's quite lightweight as well. Titanium. Well, we're not in the space race, but titanium is actually making inroads into construction now. It's got the highest strength to density ratio of any metallic element. It's got a really, really high natural resistance to corrosion, rust, and a lot of chemicals. Its coefficient of thermal expansion is half that of stainless steel and copper, and a third that of aluminium. So if you're in an environment where the temperatures fluctuate wildly, it's probably a good material to use because you don't have to allow for such large expansion gaps. Unfortunately, unlike iron and aluminium, you can't cast it. It doesn't lend itself to being cast into shapes. So it's generally rolled or whatever. And it's expensive. In comparison to the other ones, it's still expensive. You can get different colours of it. It can be anodised for colours, just like aluminium can be, and it can be coated. You can modify its natural surface, so you can have a highly polished one or a textured one. Architectural titanium, you get varieties of, say, textures on the top of it. And it does tend to be used mostly for the architectural aesthetic side of things, mostly at the moment, in general run-of-the-mill construction. There are some specialist areas. You'll find a lot of titanium when that's used in nuclear reactors, but that shows you how specialist it is. And the price really does knock it out for most buildings. So, hot-rolled structural steel in fire, what happens to them? Well, if I go back and show you, can I just get the picture? No, it melts. It melts, bends and sags. They've got a little bit of resistance, but that really relies on how big they are, how much of a cross-section they've got. Most of the ones we use haven't really got an awful lot. It's also affected by the load that's carrying them. So if they're heavily loaded, they're likely to fail in a fire. So as I say, the resistance is measured in relation to the ability of the structural section to survive a standard fire test. So there's a British standard, an international standard there, a European standard. There'll also be an Australian one. I deliberately don't give you the Australian one because that's one of the bits of research I like you to do. The strength of a hot rolled structural steel, and as you saw from the video and how they make it, they were rolling out those eye sections, etc. The strength of it falls with temperature. So the hotter it gets, the weaker it is. There's been some research the last few years that the limiting factor or the failure temperature of structural steel isn't common. It's not set, but it varies according to two factors: the temperature profile and the load, like how hot did it get, how quickly and how long, and how much weight's on the element. They can affect how long it'll actually last. If you've got a small, fully loaded hot rolled section, and you expose all four sides of it, a fire resistance, without any protection added to it, it can fail in 12 minutes. If you've got really big sections, which haven't got a lot of load on them, and they might have a little bit of protection from maybe the concrete floor slab, encasing just a little bit of it as it passes through the slab, etc., they might go up to 50 minutes. And when the perimeter is further reduced, you could get 60, but as you can see, it's still not a lot. Now, this might give an indication why we have sprinkler systems to try and put fires out as quick as we can. But there is some protection that we can put onto it. So we've got passive fire protection to insulate the structures and to keep the high temperatures away from the actual metal element, the steel element. And you can think of them as two types. There's the non-reactive that don't do something, and most of those are sort of boards and sprays, etc. And then there's a reactive type, so like an intermittent coating, because that actually under heat is like a paint. Put it on, when it gets hot, it puffs up into basically a carbon protective layer, rather like the timber, and it puffs up and gives it some protection. Thin film, these coatings, they're quite inert, low temperature. They behave just like a paint, but they swell up, a charred layer. That's what I just said, isn't it? They're quite common in the UK and Europe, but I don't know if they're so common in Australia at the moment. And then you get things which are more likely to see, the more physical ones. So you can clad it with boards, gypsum boards or fireboard, boxed around it here. They're quite widely used, but they are open to impact damage if you're not careful. And quite often they'll cut a hole through it to put a service through or something, and they won't make good. As soon as it's got a hole in it, it's not providing the protection anymore. There's two families of boards. Those are suitable for application, so you can decorate them, and those that aren't. So you can choose. There's spray protection. Here's a man doing some spraying like there. They're not as popular as they used to be. They're quite messy. You can get you spray on the wrong bits and it can float around a little bit. And they are susceptible to impact damage as well. There is this kind here, which is flexible blankets. They're really, I wouldn't consider those to be an initial design decision. I think they're more of an afterthought. They're good for really complicated shapes and that, but they're more of an afterthought for an upgrade, really. And then there's the concrete. So a bit of a concrete here. If I just come and have a little look, can I get that picture up? So there's the boards, and they're just fixed on, probably on a timber frame inside. It's even got the beginnings of a cornice up here. And this one is just painted with intermittent paint, so you can see it's hardly changed the look of the steel at all. So that's intermittent paint. Mr. Sprayman here, there he goes, and he's spraying it on, but it can be very, very messy. And then there's the flexible blankets. You can see that he's just wrapping one around there, and these are all being tied and pop riveted on. Always wonder how secure these rivets are. Now, it's probably got some of this chicken wire looking stuff underneath it as well. And the one that we like, concrete. They've been encased in concrete. Carbon steel, which is the construction steel. It's an alloy, really hard, really strong. This is where all your beams and your structural columns and that come from. You can use big plates of it for highway construction when you're constructing bridges before you put the wearing surface on. It comes in rectangular sections where you can weld them together. Most of the construction stuff is bolted, but you can weld. There's more control over the quality of bolting on site than there is welding. But they make box trailers and things out of these square sections. They do use it to do bridges and things like that as well. And of course, carbon steel makes the reinforcing bar that goes into reinforced concrete. And they do hollow sections as well. You mix carbon and ore together, and carbon steel is classified either as mild all the way up to very high, depending on how much carbon's in it. Okay, more carbon, stronger it gets. Stainless steel. Strangely, one of the oldest known materials. We all think of it as a modern one, but it isn't. Centuries ago it was used. They even used stainless steel in knights' armour. And structures they're built with it are still up to date. Because it doesn't corrode very much and it resists staining. You've got to be careful where it comes from, because there are problems with poor quality stainless steel coming out of certain countries. Some of the most famous architectural structures, the Chrysler Building in New York, that's got stainless steel used in it. Stainless steel is an alloy of several metals. The amounts can be played about with and adjusted to create different grades of stainless steel. You get the cheap ones which still corrode. Most common grade is 301. Go and look up the grades. I'm not telling you too much about grades. It's ductile, easy to weld. Ductile means you can bend and work it. Common to find it on roofing in some instances. More common for it to be used handrails, balustrades, architectural cladding, places that it's going to be seen because it's nice to see because it's so shiny. You can also use it for drainage components depending on the effluent or whatever that's going to go through the drains. If it's particular acids, etc., then you might want to use stainless steel because it'll have greater resistance. Structural steel. Basically, that's just what we call carbon steel. It's the construction type. It's the material. Look at that. That sentence ran away from that one. There's been a divorce. You can produce it in different cross sections. The common ones you see everywhere, and you saw a couple in that video coming out. You can get it to set values of strength and length, and the video again. You can change the chemical composition to achieve the right properties in the steel that you want. So it's useful. The word structural steel includes a broad variety of low carbon and magnesium steels. I mean, this is structural steel. These are I-beams and I-beams, and look, they're bolted on, and there's an I-beam as a column, and it looks like the staircase possibly is steel, not aluminium there. So interesting there. So if we look, what sort of shapes do you get? Well, these are your standard shapes. You get the I-beam here, and that's the L section, and you can get the box one as well. So flat bar, angle, round, hexagon. You twist that, you can actually make a good rebar out of that. Get sheet plates of it. You can make a channel section, or a web flange beam, or an I-beam as it's commonly called. The square tube, the round tube. You can use a T-bar. Half round, half oval, chamfered bar, and there's a rebar there. So those two together. So you order what you want, and as you saw in the foundry, they make them up for you. Oh, we're going on, yeah. This is British steel, so they manufacture. So you've got your dimensions of the I-beam you want here, or as we call it in Britain, a universal, a UB beam. And then you can see the size of, sorry this isn't very clear, but you can see the sizes down here, you can see what the weight is per metre run of it, and then it tells you the depth and width of the sections, which are these measurements here, and it'll start telling you some various bits about loads and spans as well. And standard, we'll just have a look at the grade of steel, because there are different grades of steel you can go on to. That's based on the chemical composition and the physical properties of the steel. Remember, in the refinery, they were reheating them to change its crystallised structure, etc. There's loads of different codes of practice around the world, or standards. A non-exhaustive list of grades. There's the European standards, the Japanese grade, the German grade, the Chinese grades. Be careful of those, because the steel can be bought from anywhere around the world. So you need to be able to convert these into ones you know. You can find guidance to them in the Society of Automated Engineering, and which alloy numbering system. There's an international organisation for this, the ISO, so that's probably the best place to go. If we try to decipher what an S275 is, well, the S is for structural steel, and the 275 is the minimum yield strength. And for reference, in countries that follow the European, the EN, it's one of the most common steels available. There are, of course, other standards. So there's an Australian standard, or a couple of Australian standards there. And then there's some manuals at the bottom here. You can look all those up through the library link. See what you can find from those. These are the sort of things I want to see referenced, really, and not just the recommended reading or a couple of websites. So this is the stuff that really needs to be referenced to show you've done some proper research on that. Where haven't we been yet? Oh, we've been everywhere now. That wasn't too bad at all, was it? Just to show you, I don't think I can get the pictures. It's a shame I can't get the picture, really. But you probably said that is the traditional way of making sheet lead. So they heat the lead up in a cauldron here. This is a bed of sand. They pour it out, and it's at an angle, and that starts running down, and then they follow it down to flatten it. Two blokes go walking down, flattening it, and it's collected in a trough at the other end to be recycled round. This is a typical zinc roof, not colour bond roof, that's a zinc roof. This is it's a museum in Barcelona, I can't remember, clad with titanium. That's what happens to steel beams in a fire if they're not protected. They're just bent. I mean, you can go and have a look at 9/11. Depends if you believe it or not, like me. These are stainless steel dowels, so they connect walls together over an expansion joint, but you can get it in cladding, etc. There's your structural steel, look, with all the bolt holes and flanges ready to be erected, like Meccano. Copper, well, just put some copper pipe work in there, but you can clad roofs with it. These are sections from aluminium curtain walling. Obviously, I didn't need to do that. Obviously, that's construction steel bolted down with an I column and an I beam. This lady here is working in a blacksmith shop with wrought iron. So she's making stuff out of wrought iron there. This one here is a typical portal frame industrial shed. This is the square section steel that they might make frames out of, or trailers, or depending on the size. And that one there is just a typical industrial unit. It's a steel portal frame, so that would be your carbon steel. This may be aluminium or something similar. This is a Z rail because it's the shape of the letter Z, and that's what the roof panels, which can be aluminium, titanium, stainless steel, or coated steel, goes on top of those, and they fix into these. These again are L rails or Z rails running on the side for the walls to fix to. And there's a bit of frameworking in the end, which may be steel or maybe aluminium. And notice the final fix is steel timber. Doesn't have to be, interestingly. This is obviously insulation underneath the roof. So there we go. So there's a quick overview of metals. We need to have a good look at it. Make sure you look at assignment 3 for any questions that come up from that one there. The next one that's coming up, I think I'm going to look at plastics. There aren't any major materials left, so we'll have a look at metals. We'll have a look at plastics. We'll probably have a quick look at a little bit of glass because they're already covered in materials too, and we'll touch on the sustainability element of these materials. And then we should be almost at the end of the unit, so we're probably going to have a week or two free at the end, which I think you'll be grateful of. So nice to chat to everybody. Now I have to turn it off, and I have to stop my recording now.